All right, let's do this now. All right, so we're going to write down u of t naught, the time evolution operator, the thing that moves us forward in time or backwards. All right, using the expression that we had derived last time. So let me just write down to summarize in case people are getting lost yet. All right, so this is this. Remember, this is now just a number, so we can put it wherever we like. That's the other eigenvalue. Oops. Good. All right, and we got the numbers by doing the by writing this in the basis of the full Hamiltonian, and we figured out how to write these projectors for the plus and minus states in the basis of E and G last time. All right, so we put that in. We're going to have a big old equation now. So we have cosine squared theta. Then we have cosine, sine, the thing with the E and the chi, I chi, complex conjugate down here, plus I chi, and then sine squared theta. All right, then we have the number part. All right, that's the first term, and then the second term is here. This is not right. I was just copying the other one. That doesn't that doesn't work, does it? All right, let's do it right instead. Minus cosine sine e to the minus I chi minus cosine sine e to the plus I chi and cosine squared theta. And this whole thing is times the phase. So e to minus I divided by h bar and to minus t naught. All right, and that's the whole thing. You could write this all in one matrix if you wanted to. There's nothing wrong with doing that. We're going to do it. What we want to calculate next, we can actually write in somewhat of a simpler way. So here's what we're going to do. This is our job. We want to calculate. We're going to assume that the system starts. So psi of t naught is in this ground state, the ground state of the system with no coupling. Okay, now for the way we set the problem up now, it can't do this. You could find some weird linear combination of the eigenstates of the full Hamiltonian that would give you this, sort of like a undoing of the problem. You can absolutely do that. But in our mind, what we're going to think is that we just somehow prepared it in that field-free state, right? It's the ground state without the coupling. Now the question is, what is the probability that we end up in a state? So what's the probability that psi t equals E? All right, so what's the probability that we go from G to E at time t, all right, as we are having this coupling? Okay, so that's what we're going to do. And to figure out the probability of going from G to E, okay, so the way you figure out the probability of being in a state or the being aligned along E, if you want to think of it that way instead, at time t, is this way. All right, so probability of G to E at t is this, a scalar product of the state vector at time t onto the original basis vector E, that whole thing squared to make a probability. Okay, that's what we need. This we know. We worked very hard to find the time evolution operator. Well, if we know that, then of course psi of t is nothing other than u t naught operating on G, because that was the state we started with. Right? So this is psi of T naught, ground state. Okay, so look at this. This looks almost simple, right? We have E U T naught G, the modulus squared. So what is that? That's nothing other than a matrix element of the time evolution operator. That's what it is. Right? This is nothing other than the square of U E G T naught. All right, do we know how to find the U E G element? We sure do. We just look at the bottom left element of this thing. Another way you can do this, or look at this, is we can write down this scalar product, or this, whatever you want to call it, matrix element, U T naught G. We can always square it at the end. So we know that in the EG basis, E is 0, 1. That was done last time. And since this is the bra version, we write it as a row vector. Then we have the matrix elements of U, which are all these things, but you know, when you add them together, this term will multiply all of these terms. This term will multiply all these terms. So you add them term by term. So you'll have UGG, UGE, UEG, and UEE. Notice it doesn't matter whether you do GE or EG because this is going to be modulus squared. This is Hermitian, and so this will be, you could have written GE squared, and it's the same thing. All right, and then what's G? G is 1, 0. All right, so when you work this out, you can work out from right to left, as you should do. So you get G, UGG times 1, 0, and then UEG, 0. Right, so this is going to be 0, 1 times UGG, UEG. And then now we have this times that, there's only one term left, which is UEG of T, right, which we knew anyway from looking at this. Okay, so this just tells us that all we need to do is characterize or analyze the UEG matrix element as a function of time. Okay, so we can write that down. If we just look at the EG element, the bottom left of each of these things, all right, we have UEG is just equal to cosine theta sine theta e to the I chi. Then we have this bit here. All right, so what do I want to, I wanted to simplify. There's a lot of writing. Let's make T0 equal 0, and let's let lambda plus, I guess I always leave the H bars in. I'll just leave the H bars in, doesn't matter. I was gonna make it a frequency to save me having to write H bar all the time, but. And the exponential part, minus I, lambda plus T over H bar. Then we have the next term, which is the minus one, right? Yeah, minus this one here, cosine theta sine theta, e to the I chi, and then the exponential part. Oh, I decided to put the H bars at the end. I'll do that. And to minus T over H bar. Okay, so what do we notice here? We notice that we have, we can factor out some stuff. All right, so we have, let's take the blue factoring pen. The blue factoring pen tells us that we can factor out the I chi's. We can factor out the cosines and the sines. And the only difference is we have a minus in the middle that we have to pay attention to. So let's do it. So that's going to give us cosine theta sine theta e to the I chi. All that comes out. And then what's left is, I'll put it down below, so times the exponential e to the minus I lambda plus T over H bar minus e to the minus I lambda minus T over H bar. All right, so when we consider that last equation that we had there, it looked like we were getting close to something that would look trigonometric, except that we had the exponents were not the same, even though the signs were different. Actually, the signs weren't different, and the exponents were not the same. So that's not going to help us. So what we're going to do next is we're going to write down UEG of t modulus squared. So you take that by just writing UEG and then multiplying it by itself with the complex conjugate. So that's going to give us cosine theta, sine theta, e to the I chi, all right? As you will see, that will go away soon. And then we have e to the minus I theta plus t over h bar, and minus e to the minus I theta minus t over h bar times cosine squared sine, it's not cosine squared, just cosine. I'm just thinking ahead. And then e to the minus I chi, this is the part of the complex conjugate, right? And then the last bit with the exponential. So we have e to the plus I theta plus lambda plus t over h bar minus, that doesn't change, that doesn't change. The sign up here does, so we have plus I lambda minus t over h bar. Okay, this is a big equation. You can obviously factor out these. These terms, as you know, hope you can see very nicely, go away, as you might expect. All the kind of complexness is going to go away because we're taking the modulus squared here. All right. What I'm going to do is I'm just going to sort of rewrite it in a slightly different form, but I'm not going to do all the steps to get to the final equation. That involves us to unpack these thetas. Remember, the theta was defined sort of indirectly using the tangent to theta of it. And so it's tedious. I did it once, I don't know, when I was a grad student maybe. And if you're interested in solving the algebra, go for it. It's totally doable. You just have to remember some trigonometric identities. There's no science in it. It's just math. And so that's great for math, but it doesn't really help us learn anything about science. So I'm going to skip it. But what you do, there's no magic though. There's nothing, I'm not making any approximations or any Taylor series that I'm cutting. This is just a different way of writing this complicated equation once we put in what the thetas are. Right? But when you do that, then you find that this thing is actually equal to the following. 4 v squared divided by 4 v squared plus epsilon g minus epsilon e squared. Of course, you could write this the other way around because you're squaring, it makes no difference, times sine squared of all of this. The square root of epsilon, just make sure I get the order here, g minus epsilon e, oh, that's squared, so it doesn't matter there either, plus 4 v squared. We'll recognize this from the eigenvalues. And this outside the square root times all of this, you have t over 2 h bar. All right, so what you see is that this looks like sine squared omega, or energy divided by Planck's constant, so that's a frequency, with a half because of the sine squared. Sine squared doubles the frequency, and so here we're having the frequency, so you get back the same frequency of the gap between the two that you expected to have, and then times time. Okay, so you see the ingredients that you might have expected, which is that this is going to oscillate as a function of time. And it oscillates with a frequency that's exactly the gap frequency given by the two. The magnitude is out here. This is the magnitude. Right, and this is the oscillatory part. And you can see the amount of oscillation you get, this magnitude, depends on basically the relative amount of coupling versus the initial what we call the detuning, the difference in the energies between the two states without any coupling at all. Okay, so this is actually a really, maybe it looks like there's a lot of terms here, but there's really not much. There's only the parameters in the Hamiltonian. and that's it, and time. And it's sine squared. As you expect, this should be positive for all values. It should not go, and the other question is, can it go greater than 1? So that's an interesting question. So you can ask how can this be, can this amplitude actually be greater than 1? So we're going to look at that in a minute. Okay, the first thing that we're going to do is we're going to define a frequency, just like I described here, right? If you look at this, you see t times something in a sine, so you know that everything else is something like a frequency, right? And the way that this is done historically, remember this is the same thing as delta, all right? So we're going to define omega r, as you'll understand why later, 1 over h bar, like I said, times the stuff inside there. Okay, so then that ends up just replacing, you can just replace all the sine squared business with this theta omega r. And the reason why this is called omega r is because the first person to explain all of this was someone named Rabi. And this is called a Rabi oscillation. So what you do is you turn the field on. If you think about how you might do an experiment like this, you have the probability of being in E given that you were in G T naught as a function of time, all right? And this is time. And what's going to happen is if we plot the time in sort of units of the Rabi frequency, then what's going to happen is we're going to have oscillations that look like this, just like you expect for sine squared, right? And the time in this reduced unit will be equal to pi, right? When sine squared goes to pi, then we'll have the maximum. This is pi over 2. And then 2 pi is here. Sorry, I said sine squared is the maximum. I don't mean that. It's because this factor of 2 changes that. All right, so normally sine goes to 1 at integral numbers of the pi, of when this thing is pi. So we're keeping the factor of 2 in there. So that's why this goes when the whole thing has when t times Rabi frequency is pi. Divided by 2, it'll be pi over 2, and that's where sine maximizes. Okay, and then you see the next one over here is 4 pi, and so on. So it's sort of like half of what you're used to from a sine function, just because of this factor of 2. All right, so what this says is that you can get, if you weight an amount pi in this reduced time, so pi, when t times the Rabi frequency is equal to pi, then the system will be maximally converted into the excited state of the uncoupled two-level system, right? But as that field stays on, it'll keep oscillating back down again, and back up, and back down again, and back up. That's not shocking. All it's saying is that G and E are not eigenfunctions or not eigenvectors of the full Hamiltonian, so you expect oscillation, just like we have been working out since the very beginning of the class. But in practice, it turns out, amazingly enough, you can do experiments like this, where you have a system sitting along doing nothing. It's in the ground state for sure of the field-free Hamiltonian, and then you come along and you turn on a field, a constant field, and leave it on, right? And then you can actually turn it off. And what this is saying, now there's some issue about how you turn it on and turn it off, no question about that. And we'll see that the time that we turn it on or off may matter, and it depends on the frequency difference between the two states, right? But if the frequency difference between the two states is not that big, and we can turn it on super fast, it turns out not to matter. And that's exactly what the case is in NMR. Frequency gaps in NMR are, for a proton in a 500 megahertz NMR, it's literally 500 megahertz, which is not a high frequency. You can easily turn on a radio frequency pulse much faster than that. All right, so you can put a field on, and then you can perturb the system. And then you can leave that field on, and you can turn it off suddenly again. And that allows you then to have this phenomenon occurring when the field is on, as long as you turn the field on fast. So like here's our field chart down here. And if we stop the field now, the system will continue evolving like that, because as soon as we turn off the field, if it's in the excited state, it stays in an eigenstate. And what we learned is that the probability of the different states will not change. All right, so then what we have here, if we had turned it off at this spot, right, well then what would happen is the system would stay in the ground state. And this idea that you can turn a field on, drive a system up to an excited state, and then back down to the ground state and leave it there was termed in the older era, so-called Rabi flopping. The idea you can switch the state up and down, up and down, up and down, just by changing the duration of the field that's on that's coupling those two together. And this is really the basis for a lot of the spectroscopy in NMR. And in more modern times, of course, NMR still happens. But people use tricks like this when they want to do quantum information processing. Now let's take a look at this amplitude real quick. Here's the amplitude, right? The amplitude of the maximum, so let's call that A. A is equal to 4 v squared over 4 v squared plus delta squared. So let's take a look at this amplitude, okay? When we, for example, make the detuning, the initial energy gap between the two states go to 0. Well, if we make the energy gap between the two states go to 0, delta squared goes to 0 as well, and this amplitude becomes 1. So in this case, A equals 1. What that means is, hopefully that's clear, you can drive to 100% the system to the excited state in the field-free case. All right? Now notice what happens. Delta squared is always positive, right? So since delta squared is always positive, that means no matter what delta is, the denominator is always larger than the numerator. That means, so when the initial state had a delta that's not equal to 0, well, it's greater than 0, say, then the amplitude is less than 1. Right? In other words, you can't drive the system all the way to the excited state if the field-free energy levels are not equal to each other. Okay, and that just gives you some insight about that. And we'll see later on what happens if they are different when our field oscillates. If our field oscillates, then you can do all kinds of different things because now our field will have a frequency associated with it. So then there can be resonance, and that resonance is going to be obviously very important for spectroscopy. Notice there's no time dependence implicit in the we didn't put any time dependent explicitly into the potential term here. All right, so there's no resonance to think of. Another way you could think of it maybe is better. As I'm saying this, it kind of occurred to me. You could think that this here, okay, has a frequency gap of 0. So our field also has a frequency of 0, right? It's a constant in time, which means it has no frequency, or the frequency of 0. It's DC is what some people might call. It's a DC field, it has no time varying amplitude. Now, of course, if I really turn the pulse on or the field on and off again, the frequency domain version of this, in fact, would have frequency components, right? The way I could understand that is to do the Fourier transform of this. The Fourier transform of a square, if I look at the intensity of the Fourier transform, it's a function that looks like this. And we're going to see this function many times because this is one of the most important functions since it describes energy transfer from one state to another state. This is a function that has the form sine squared x over sine x over x squared. The reason I did it quicker is because it's also called sinc squared x. This is x. Sinc stands for, I only know it in French, sinus cardinal. So somehow it's the cardinal sign that we call this. And it's a function that comes up a lot because it's the Fourier transform of a square or a rectangle. Okay, so that's it. So we have a two-level system with no field. Obviously, when the field is, and we put the system in the ground state of that, and we consider how that system evolves when the field is on. We're not talking about turning it on. We'll come to that later. We're just imagining that somehow we can do this. Then what we see, as we should expect, is that the probability of going from the ground state to the excited state evolves. All right, and that probability we've figured out by solving or determining the time evolution operator in terms of the knowing how it operates on its own eigenbasis, but then writing it in the basis of the uncoupled state so that we could just read off of that matrix this transition probability here. All right? And of course, as you can get, I mean, just saying the words, you can sense that this is moving in towards the direction of spectroscopy because we're thinking about how a field can change the probability of occupying one state or another state. We see the frequency here. Now, one thing I want to make sure of sort of clear about this that's kind of cool, it doesn't happen in most conventional optical spectroscopy. When we did this, we discovered that there are Rabi oscillations, right? A Rabi frequency, which we defined here. And maybe it's not too surprising that we see the field-free detuning here. But we know that the energy gap between the two states depends on the coupling, right? So if we think of the coupling as arising from some external influence like a field that we apply, then what this tells us is the Rabi frequency itself is a parameter we can vary in the lab, right? By just changing the strength of this field. That's very interesting. Of course, that's exactly what happens in NMR. You have spin up and spin down. They have the same energy normally. You turn on a magnetic field like this and they split. The strength of the magnetic field determines the amount of splitting, and that determines the chemical, not the chemical shift, but the Larmor frequency. Then the environment and what all the other stuff determines the actual chemical shift. All right, and so just the fact that you have spin up and spin down with different energies comes from this right here. And you know that if you use a 500 megahertz NMR, the difference between up and down will be 500 megahertz nominally. Of course, it depends on all the little experimental details. Whereas if you used a gigahertz NMR spectrometer, then the frequency gap would be about twice as much. All right, and the reason why that's useful is because you stretch all of the peaks away from each other, and you gain spectral resolution for your whole spectrum when you go to a higher field strength. And that field strength is right here. Okay, so this is a way of linking things that we know from conventional NMR spectroscopy to thinking about what's microscopically going on when we have levels that would not be different in energy, but become different when we put a field.